Hello everybody, this is the spring break review video in which I go over every single question on this. It's probably going to be pretty lengthy because there's a lot of questions here. And on this video, I want you guys to review your answers and answer those appropriate corresponding reflection questions on pupil path. Alright, and here we're going to start with number 1. Here we have a 200 Newton block at rest on a horizontal table. So 200 newtons right off the bat they give us is its weight, not its mass. So this is our force that's going down, its weight. A force of 40 newtons is required to start the block moving. Okay, so F equals 40 newtons. Another key word is that it's at rest. So that means we're in equilibrium. That means both the vertical and the horizontal forces are all balanced out. Our weight here is supported by the normal force, whereas force applied is balanced out by the force of friction that's causing it to stay still. So writing these things off to the side, normal force equals 200, which equals the weight. The force applied equals 40 newtons, which equals the force of friction. We're looking for the coefficient of static friction. So what is mu? Well, in the attached reference table, you're going to see that mu is only present in this equation. Force of friction is equal to mu Fn. We already have our force of friction. We're looking for mu, and our normal force is 200. 40 divided by 200 will give us 0.2. There we go. Number 2, sketch the shape of the plot of a mass versus distance and gravitational force versus distance for a rocket ship moving away from the Earth. We should already know that right off the bat, mass doesn't change, okay? Regardless of how far away you're moving from the Earth. It's the weight, it's the gravitational force. Weight is dependent on gravity, mass is not. It's dependent on the amount of particles you have in your system. It's not going to change when you move away from the Earth. So this should stay constant, regardless. Now gravitational force, on the other hand, versus distance, we're going to think of this equation, the big G. Look how distance is in the denominator. It's also squared. So we should think it's the inverse square relationship, like that. So you start off with a high force when you're short distance, and then as you increase that distance, it decreases the force exponentially. Alright, now number 3. 2 cars are at rest with a coiled spring between them. One car is 100 kilograms, the other is 75. When the coiled spring between the cars is released, the cars are pushed apart. If the 75 kilogram car attains a speed of 4 meters per second, what speed does the 100 kilogram attain? Okay. And they're at rest. So this is a little bit about conservation of momentum. So that the total momentum before the incident equals the total momentum after. So P before equals P after. 2 cars are at rest. So before you release the spring, everything's at rest here. So there's no momentum. It's not moving. Whereas afterwards, the 2 cars separate. M1v1F plus M2v2F. Let's remember that momentum here is equal to m times v. So we need to break up our total momentum after into each of the 2 objects. Okay. So 100 kilograms times v1f, which we don't know, but of the other car, it's 75 kilograms here, times 4 meters per second. v1f equals 3 meters per second. Okay, number 4. A 300 kilogram car skids on a horizontal wet concrete road. What is the force of friction? Okay, force of friction is given as this. We need to look up the mu value of our surface here, rubber on wet concrete. Why is it rubber? They didn't mention anything about rubber, but we have a car. Cars have rubber tires, so that rubber tire is going to be in contact with the wet concrete road. You need to look that up on the reference table. And so you get that mu is 0.58 times your normal force, which is 300 kilograms, times 9.81. Gotta remember that when they give it to you in kilograms, you need to multiply by 9.81 in order to convert it into newtons. So plug and chug, and you should get 1648 newtons as your answer. All right, number 5. A hunter fires a bullet from a rifle. What is the total momentum of the rifle, hunter, and bullet after the rifle is fired? If the momentum of the bullet is 1200 kilogram meters per second, what is the momentum of the hunter and rifle? Okay, so again, conservation of momentum. Here we have a bullet inside the rifle. The total momentum equals total momentum after. Now, before the explosion happens, here we have the bullet inside the rifle. So these two objects are together and at rest. Nothing is happening. So your total momentum is equal to 0. So that's your answer for the first question of this. 0 kilograms meters per second. Now, if the momentum of the bullet is 1200 kilograms meters per second, so that means our momentum after is broken into momentum of the bullet plus the momentum of the hunter and the rifle. Okay, so look how it's equal to 0 here, because our momentum after is equal to momentum before. So notice that these should easily cancel each other out, but opposite in direction. So the momentum will also be 1200 kilograms meters per second. Okay, here we have a velocity versus time graph. Okay, so 1, 2. Okay, at time equals 1, we have this, then we have this, and this. So here we're looking for the distance traveled from t equals 0 to t equals 3. So when given a velocity versus time graph, you need to find the area under the curve. Or you could use this graph to pick out the values and use kinematics. So I'm going to show you here the graphing method. So because we don't know what our acceleration is, we can use the graph method in order to figure it out. Otherwise, if they give you the acceleration, you can use the kinematics method, because all those equations require the use of acceleration. Okay, so our shape of the graph here is a triangle. The area of a triangle is equal to 1/2 base times height. So in here, our base is 3 seconds with a height of 6 meters per second. So plug and chug, 3 times 6 is 18, times half is 9 meters. So within this time interval, we traveled about 9 meters. Okay. Now number 7. A car moving at a speed of 8 meters per second enters a highway and accelerates at 3 meters per second square. So VI equals 8 meters per second. Acceleration is 3 meters per second squared. How fast will the car be moving? So VF is a question mark. After it is accelerated for 56 meters. So there's an equation just for this. All right, and it's VF squared equals VI squared plus 2AD. Plug it in for VF. Okay. Squared plus 2 times 3 meters per second squared times 56 meters. And after you solve, you should get a velocity of 20 meters per second as your final answer. Okay, that's it for number 7. Now number 8. How much work is done? We're looking for work when a ball weighing 20 newtons is lifted a vertical distance of 2 meters. Okay, so remember that work is equal to force times distance. The force that we're exerting is equal to the weight of the object, because we need to either match it or exert more force in order to lift it up against gravity. So 20 newtons times 2 meters, W equals 40 joules. Okay, number 9. An object moving at a constant speed of 4 meters per second possesses 160 joules of kinetic energy. Okay, what is the object's mass? KE equals 1/2 mv squared. 160 joules equals 1/2 m times 4 meters per second squared. And so we're looking for m. And you should get that m is equal to 20 kilograms. Okay, so that's our final answer for these questions. Number 10, a 1 meter spring is stretched to 1.2 meters by a force of 6 newtons. So the force exerted on the spring is 6 newtons. We are looking for K, the spring constant, and the difference the spring has stretched, the extension or compression, is from 1 meter to 1.2. So the difference here is 0.2 meters, and that is our x. We need to figure out the spring constant, so Fs equals Kx, 6 newtons equals K times 0.2 meters. Alright, you should get that K is equal to 30 newtons per meter. Alright, number 11, straightforward. A projectile takes 2 seconds to reach the peak of its parabolic path. Okay, or let me do it here. So 2 seconds to reach from the bottom to the top right here. So if it takes 2 seconds to reach the top, then it should also take 2 seconds to reach the bottom. So the total time it spends in the air is 4 seconds. Alright, number 12 is one of those tricky questions, and here we just got to remember 2D kinematics for this one, where we have an angled projectile. And remember that horizontal and vertical velocity had to be treated differently. So x direction stays constant because of no air resistance. But the y, on the other hand, changes because of gravity. Because gravity's a thing, guys. Alright, so based on this, the horizontal velocity will stay a constant 10 meters per second in our ideal world. Vy, on the other hand, will slow down until it reaches the top and then speed back up going down. So, and this thing is also symmetrical. So t equals 0, 30 meters per second, is also the same at t equals 6. Now, right at the middle, where it reaches the peak, its vertical velocity is 0 at the peak. Remember that. And then from there, all it is really using kinematics to solve for the remaining values and understand where it's symmetrical to. So I'm going to calculate for t equals 1. Okay. So we know that Vi equals 30. Vf we don't know. A is negative 9.81 because we're going up. And distance we don't know, time we don't know, but that's alright. Oh, actually time we do know, and that's 1 second. Alright, so we could easily do this. Vf equals Vi plus AT. Vf equals 30 plus negative 9.81 times 1. So VF here is approximately equal to 20 meters per second. And it's the same thing at over in t equals 5. Now, if we follow the trends, let's just safely assume this is going to be 10. You can also do the calculations following the sample I did, just to verify that it is actually these values. All right. Now, number 13. Projectiles fired at an angle of 30 degrees. The vertical velocity of the object is 10 meters per second. The horizontal is 20. How far will the object travel in 3 seconds? So we are looking specifically for how far. So that's in the x. So that means we need this, horizontal velocity. In the x, we have no acceleration, so our equation is just v equals d over t. So our velocity here is 20 meters per second because it'll stay constant. Our dx we're trying to figure out, and t is 3 seconds. dx has to be 60 meters. Number 14, draw and label the velocity, centripetal acceleration, and centripetal force vectors for this object moving in a circle. So in each of the 3 examples, we should take note of the direction of the arrows. So because we're moving clockwise, our velocity should be like this, and our acceleration and force should always be towards the center. Same thing here. So you should remember the velocity will go out like this in a straight line out of the circle, and this will always be centripetal acceleration and force. Alright, now number 15. We're more than halfway through. An object with a speed of 2 meters per second has an acceleration of 4 meters per second squared. What is the radius of the circle in which the object travels? We have speed and acceleration, so we're talking about a circle as well. So we're looking for r. AC is equal to 4 meters per second squared. And v equals 2 meters per second. All it is AC equals v squared over r. 4 equals 2 meters per second squared. And you get that r is equal to 0.5 meters. All right. Okay, 16. Calculate the forces between 2 electrons that are separated by a distance of 2 meters. Is this a force attractive or repulsive? So first of all, 2 electrons we should already know is repulsive because like charges repel, opposites attract. And now we got to calculate this. So we're talking about electrical forces. Fe equals kq1, q2 over r squared. All right. K is the electrostatic constant. It's on the front of the reference table. This is 8.99 times 10 to the 9th newtons dot meters squared over c coulombs squared times elementary charge, because each of these are electrons and they have the same charge. So I'm just going to put it right under here. 1.6 times 10 to the negative 19 coulombs, and we square that because both charges are the same. And we put all of that over our radius squared, 2 meters squared. Plug and chug. You should get an answer of 5.75 times 10 to the negative 29 newtons. So that's a really small force. And anyway, a distance of 2 meters is pretty big for 2 electrons. Very weak force. Okay, now number 17. We have to explain why a charge of 1.6 times 10 to the negative 20 coulombs is not an allowable charge. So for number 17, you should keep in mind the elementary charge is the smallest possible charge, and this is the value of it, to the negative 19 coulombs. To the negative 20 is smaller. So this here is smaller than elementary charge. Excuse me, sorry, I'm sneezing. It's allergy season, guys. Be prepared for a sick mapoi. Alright. Now number 18 is the last one I'll do on this page. Draw the electric field between two positively charged spheres. You must draw at least 5 electric field vectors. So 2 positively charged spheres. Remember that positives radiate happiness, negatives suck in happiness. And that like charges repel, so these lines will curve away from each other. So yes, they'll be pointing outwards. But when you try to combine them near each other, they're going to curve away like this, so that the field right in between them is 0 because it cancels out. Okay? Just like that. Alright, now we're up to number 19. After a model rocket reached its maximum height, so we have an object being launched up, and it reaches its maximum height all the way up here. It then took 5 seconds to return to the launch site. So it goes up and it comes back down. So this part, the way back down, took 5 seconds. Now we're at the peak here. And remember that the peak, the velocity here is equal to 0. Alright? And since we're working vertically, we're subjected to gravity, and its acceleration is 9.81 meters per second squared. Alright, now we're looking for the maximum height reached for by the rocket. So we don't know what's this distance right here. So we gotta use kinematics. So d equals question mark. We could start from the top, meaning our initial velocity is 0 meters per second. T equals 5 seconds, and a is equal to 9.81 meters per second squared. So we're going to use this one. D equals VIT plus 1/2 AT squared. We're looking for D, so this already crosses out to 0. So 1/2 9.81 meters per second squared times time squared, V 5 seconds squared. And so D will then equal 122.625 meters. Okay. Number 20. An object with an initial speed of 4 meters per second, so VI equals 4 meters per second, accelerates uniformly at 2 meters per second squared in the direction of its motion for a distance of 5 meters. What is the final speed of the object? So we're going to use this equation. Okay, we're looking for VF, 4 meters per second, squared plus 2 times 2 times 5. VF will then equal 6 meters per second. That's our final answer. Number 21. A student throwing a baseball horizontally at 25 meters per second from a cliff 45 meters above the level ground. Approximately how far from the base of the cliff does the ball hit the ground? So here we have a person throwing the ball off the cliff. It goes like this. So remember that even though this is a horizontal velocity, we also have to think vertical velocity as well. This is a 2D problem. We're figuring out how far from the base of the cliff does the ball hit the ground. Okay, so I'm going to do this space over here. So we got to do our T-chart. Okay, so V equals 25, dy equals 45. Remember that we also have a vertical velocity, 9.81. Vi is 0. Because remember, in terms of throwing things horizontally, your initial velocity is only horizontal. There's nothing vertically happening at first. So it's like almost you're dropping the object in the vertical direction. So the one thing they also share is time. So we need to figure out what the time is before we even figure out the distance in the horizontal direction. So we got to use kinematics. It's a 2-step problem. So we're going to do D equals VIT plus 1/2 AT squared to figure out what T is. Because our initial velocity is 0, This will already cancel out to 0, and we're getting D equals 1/2 9.81 times T squared, which equals 45. You plug in for T and calculate for it, and you get 3.03 seconds, which you're then going to plug in for our horizontal equation, V equals D over T. So this is dx and x. So 25 meters per second equals dx over 3.03, and you get that dx is equal to 75.75 meters for number 21. Number 22, a 0.1 kilogram model rocket's engine is designed to deliver an impulse of 6 Newton seconds. If the engine burns for 0.75 seconds, what average force does it produce? So number 22. So the mass is equal to 0.1 kilograms. The impulse J is equal to 6 Newton seconds. The time is equal to 0.75 seconds, and the force we don't know. This is straightforward though, as J equals Ft. Impulse J is equal to force times time. 6 equals F times 0.75, divided by 0.75 on both sides, and you get, should be 8, yeah, 8 newtons as your answer for number 22. Number 23. During a collision, an 84-kilogram driver of a car moving at 24 meters per second is brought to rest by an inflating airbag in 1.2 seconds. What is the magnitude of the force? So this is another momentum impulse question. So mass is 84 kilograms. Velocity initially is 24 meters per second, brought to rest, Vf equals 0. Time is 1.2 seconds, and we need to know the force. So this is an Ft equals m delta v, the change in momentum. So this is also on the reference table, where force times time is equal to change in momentum. And when you change the momentum, you're changing the velocity specifically. So let's plug this in. So it's 1.2 equals 84 times a change of negative 24 meters per second. Now remember that change in velocity is always Vf minus Vi, so 0 minus 24 is negative 24. This matters so we could figure out that our force is acting in the opposite direction. Especially when you're slowing down or stopping something, it acts in the opposite direction. You should get a force of negative 1680 newtons as your answer. Alright, negative indicating it comes from the opposite direction, especially to stop something from moving. Alright, 2 more questions, guys. We're almost there. Can I cram it into the little space that I have left? We'll see. Alright, number 24. A constant force of 1900 newtons is required to keep an automobile having a mass of 1,000 kilograms moving at a constant speed of 20 meters per second. What is the work done in moving the automobile a distance of that much? That's too many words for something that's so simple, honestly. So we're looking for work. They gave us the force, 1900 newtons. They gave us the mass of 1,000 kilograms. And they gave us the distance of 2,000 meters. When honestly, work is just force times distance. So 1900 times 2,000 is equal to, oh boy, that's a huge number, 3,800,000 joules. 3,800,000 joules. That's a lot of energy. Okay. And finally, our last question on this review. Number 25. Calculate the resistance. So R is a question mark. We're looking for resistance R of 1,000 meter long copper wire. So length is 1,000 meters with a cross-sectional area of 3 times 10 to the negative 5th power meters squared, And our material is copper, so we need to look up the resistivity value for copper on the reference table. And copper is 1.72 times 10 to the negative 8th ohm meters. And the equation for resistance is R equals rho L over A. Not P, rho. It's Greek. 72E negative 8 times 1,000. I'm just cramming everything here. 3E negative 5. Plug it in, and you should get the answer. And the resistance is 0.573 repeating ohms. And that is the answer of the final question. All 25 questions done, all for you guys. Go through your answers, check which ones are correct, check which ones you really need help on, and answer those reflection questions. I expect them done by Monday. Take care, guys. Have a good weekend. Done. And please apologize for my sniveling. Now I'm starting to have a runny nose. I hope I don't get sick this weekend. Anyway, I digress. Bye.